Today I'm going to show you guys how these variable speed motors actually work. We're going to go over all the wiring here. I'm going to show you a basic troubleshooting process, and I'm also going to show you how to test these modules on the motor without an actual ECM tester. There's a little jumper trick you can use, and I'll show you that when we get to that point. So starting from the very beginning, I have my power cord here coming into my shutoff switch, and we have a 120 volt leg coming into a door switch here. So I pulled this whole thing out of a furnace. Air handler's not going to have that, but the 120 volts goes through that switch and goes directly to the control board. Now that black wire coming off our door switch, we're going to connect it right here on this terminal where it says line. That's our line voltage, our 120 volts coming in. So I'm going to go ahead and make that connection there. And you can see right up in here, we have line neutral. That's where our white wire is going to go. And that's going to come directly off the switch itself. So I'll just go ahead and I'll plug that in. So these two wires supply the 120 volts we need to run the blower motor itself, and any other high voltage components that might be in the unit. So in the case of the furnace that I ripped this out of, that would be the inducer draft motor, hot surface igniter, and so on. Now, one more component we need to get high voltage to is our step-down transformer. So this is going to take the 120 volts we're feeding into our board and step it down to 24 volts that we can use in our control circuit. So that's the voltage for our thermostat, the terminals on our control board that send out the heating and cooling coils and so forth. So to do that, we have a transformer hot. We're going to go on there and we're going to run that to our primary side on our transformer. So this here's our primary side, and we're going to feed the 120 volts right into there. Now we also have to run the neutral from the primary side back to the control board again. So I'm just going to go ahead and plug the neutral in there. And then back over on the control board, we have our transformer neutral connection right here. Now we have to run our 24 volts from the secondary side of our transformer back to the control board. Now to do that on this particular setup here, we have a Molex plug with a bunch of wires coming off of it. Most of these wires are for the safeties in the heating circuit, which we're not going to get into today. I do have a video that goes deep into heating circuits on furnaces. You can watch that if you're interested. But we're just going to hook up these red and blue wires, which is 24 volts from the secondary side of a transformer that feeds to our control board, which we can use to go ahead and then control our system and run our blower motor. So on the secondary side, I have 24 volts there. That is my connection. I'm going to connect that red wire on there. And this is my common. I'm going to put the blue on there. And then I'm going to go ahead and plug my Molex plug into the board. It only goes in one way. And that's it. We have our 24 volts for the whole control circuit. Now, all these ECM motors, they have two Molex plug connections. On this one here, this 5-pin connection, this is for our high voltage. These Molex plugs up here, this 16-pin connector, that is all low voltage DC electronic signals. It's communication between the module on the motor itself and the control board. So a lot of data passes back and forth between the control board and the motor module. It's timing, blower speed profiles, synchronization signals, and so forth. So these motors, they always get a constant power supply all the time. So they come on a Molex plug. We're going to put this Molex plug in here. The black wires are 120 coming in. The white is our neutral. Green is our ground. You see this yellow wire here. It's a jumper. Some motors can be converted from 115 to 230. So they can go in a furnace or an air handler. And you can see here the sticker right on the side of the motor. It's only rated for 115. So that jumper doesn't do anything. I think they just put them on all the Molex plugs. So we're going to go ahead. We're going to put our Molex plug in there. And again, it only goes in one way. Now over here, we have a pin that says CIR-H. That's our circulator blower or blower motor. That's our hot, or 120 volts. So black wire from that Molex plug will go right there. And then our neutral goes back to the circ N. That's our neutral there. Now, this is where things really change when it comes to the ECM motors and control boards versus the old stuff we're used to seeing. So you see these 4 diodes here. And what this is it's a diode bridge or a rectifier. This takes the 24 volts in the control board and sends it through these diodes to turn it into a DC voltage. So when our transformer is putting out 24 volts, it does it in a sine wave. We've all seen this before. It has a peak at 24 volts positive, then a trough at 24 volts negative, and it just keeps fluctuating back and forth. this diode bridge does is it kind of cuts that sine wave right in half and just keeps the positive portion of it. So you can see the change in how that wave looks. It goes from 0 volts up to 30 plus volts, back down to 0, 30, 0. So it's still fluctuating like a sine wave, but now this is the beginning of DC. So this is called a pulsating DC wave. So I have my multimeter set to DC volts here, and I'm just going to show you the voltage coming out of this rectifier here. Now, I don't suggest you start putting multimeter pins on a control board unless you really know it well. I mean, I studied this before I did it. It's very easy to fry these boards out. But you can see the rectifier takes our 24 volts AC and turns it into just about 39 volts DC. Now, these variable speed motors, they're very precisely controlled. And in order to get that precision control, we need a very clean and stable signal. And this is the beginning of it. But this is too sloppy, this pulsating DC wave. It's fluctuating too much. We need to clean it up even more. So our next step, it comes to this brown cylinder here, and that is a filter capacitor. What it does is it takes that DC pulsating wave that's coming off of that diode bridge, and it turns it into a nice smooth, what's called a ripple DC wave. So it's smoothing that signal out. Now you see this black card here, it goes there next, and that is a voltage regulator. So it takes that modulating DC up and down and turns it into one single stable, steady voltage. So you can see the voltage output here on this voltage regulator is a nice steady 15 volts DC. And that 15 volts DC goes straight to the microprocessor. And this is the brains of the system. This is what's monitoring everything, making all the decisions, and sending the signals to the ECM variable speed motor module in order to run whatever blower profiles it deems necessary for the condition. Now, this microprocessor is communicating with the module on the motor itself through all these white wires here. So what we're talking about here is like a low DC voltage power that powers the ECM's module's logic. We have speed and torque commands, what airflow targets to hit. We have feedback and status. We can keep track of the motor RPM, the torque load, fault statuses, things of that nature. And so there's constant communication and readings back and forth between the module and this microprocessor. So that's why we go through all the trouble of cleaning these signals up and making them nice and steady, because any fluctuations can lead to misreadings between the module and the control board. Now, the orange and blue wires you see here is something separate. This isn't coming from the microprocessor. This is actually coming from all the way back in the beginning where we started with the diode bridge. Our 24 volt signal off the transformer splits off before it hits that diode bridge and goes through its own cleanup process. So it goes through another cap, it goes through another diode bridge of its own, and this sends a 5 volt DC electronic signal that acts like the heartbeat of the system. It's a timing sequence signal. So you got all your logic and sequence going on at the microprocessor, you got logic and sequences going on in the control module on the motor, and this timing mechanism keeps them both lock in step. They're not drifting away from one another and miscommunicating. Now, the low voltage isn't the only thing that needs to be cleaned up. These motors, when they're running, their electronics rapidly switch the power on and off thousands of times a second, and that switching creates electrical noise that can travel back into the wiring of the house itself. So you might see something that looks like this. Now, it looks like a transformer, but it's not. It's called a choke, and it helps cancel out all that electrical noise from that constant switching back and forth so it can't make it back into the wiring of the house itself and affect other electronics like Wi-Fi routers, radios, TVs, even other smart devices in the home. So 120 volts we grabbed off the control board that we plugged right into the Molex on the motor itself actually runs through this choke to filter out all those high frequency noise from the switching. Now, before I open up the ECM module and show you everything that's going on there, I'm just going to start with the troubleshooting process at this point because we're going to open up that module anyway. So one of the first things I'm going to do is I'm going to actually check and make sure I actually have 24 volts on the system. So to do that, real simple, just go between R and C on the control board terminals, and I'm reading about 29 volts there. So I know I'm getting low voltage to control board, which means I should be getting low voltage through that diode bridge, the cap, the voltage regulator to the microprocessor. And as long as I have a signal for the blower to turn on, that signal should be sent through those communication wires to turn on the motor. So what I'll do next is I'll just take a jumper and I'll go between R and G just to give it that signal. So the purpose behind what I'm doing here is I'm making sure the thermostat or any wiring to or from the thermostat is not the problem. By jumpering it out, I can eliminate that as a possibility. So in this case, if the blower starts like you see here, I might start looking at the thermostat and the wiring. Now let's say the motor didn't start. Next thing I'm going to do is I'm going to shut the power off. I'm going to disconnect that 5-pin Molex that the 120 volts is going to. Now, I always shut the power off whenever I'm connecting or disconnecting these Molex plugs, especially when I'm working around pretty sensitive electronics like we are here. Shut the power off, and we will pull this plug out. So once I got my plug pulled out, I'm going to make sure I'm in alternating current voltage, and I'm going to hook up to the black and the white wire, my leads. And then once I'm set up, I'm going to go ahead and turn the power back on. And as you see, I'm verifying that I do have 125 volts going to the motor. I'll then shut it back off and then reconnect the Molex plug. Now, if I'm not getting power at my motor, next thing I want to check, so I want to make sure the board itself is putting power out. So I'm going to go ahead and check between the hot wire on circulator and the neutral. And I'm getting 125 there. If I wasn't getting 125 there, I would start suspecting the control board is bad because I already know I have 120 volts coming in. Otherwise, I wouldn't have 24 volts down below in my earlier test. Now, if I was getting 120 volts off the board, but I'm not getting it at the motor, then it's time to ohm out those wires. So to ohm that wire out, I went ahead and I shut the power off. I disconnected the Molex plug from the motor, and I took the hot wire off the control board that feeds the Molex plug, and I put my multimeter in the ohm setting. You want to test your leads. You want to make sure you're reading 0. If you're reading anything higher than 0, it's time to replace your probes. So you're seeing good there. So what I do now is I want to go ahead and put one lead on the black wire from the control board, one lead on the black wire in the Molex plug, and you should read 0 ohms if you have a good wire. If you're reading high resistance or you're reading OL, the wire's the problem. Now you can also do the same thing with the neutral. So here's our neutral wire. We'll go ahead and put one probe in there. We'll go ahead and switch over to our neutral on the Molex plug, and we should see the same thing. We should see 0. Now at this point, if everything checks out and the motor's still not starting up, what I would do here is I would just disconnect my 16-pin Molex. I would hook up an ECM tester directly to the module itself. And basically what I'm doing here is I'm using the 120 volts directly from the control board to run the motor. And the ECM tester is just giving the module the signal to run. If the motor does run at that point, then the problem may be with the harness itself or the control board. If it doesn't run, then the problem is likely with the module or the motor. Now, in the beginning of the video, I mentioned there is a jumper trick you can use if you don't have an ECM tester, and I'll show you that next. So in order to do this jumper test, we're going to shut the power off and we're going to disconnect the 16-pin Molex from the control board itself. Now, this blue wire here, that goes to pin number 1, and the orange wire is pin number 9. So on the blue side, it's 1 to 8. On the orange side, it's 9 to 16. Now I'm going to take a little piece of thermostat wire. I have a little bare spot that I put in there so I can attach alligator clips to it. And what we want to do is we want to go from pin 1, which is where that blue wire is, to pin 3. So I'm just going to throw that jumper right in there to pins 1 and 3. Then I'm going to take another jumper, same thing, and I'm going to jumper between pins 15 and 12. So that orange wire is pin 9, all the way down at the other end is pin 16. So 15 is just before that one, and then you count back to 12. Now, it's very important you get the right pins. It's very easy to fry the module if you don't get this right. So if you're not seeing exactly what I show you here, stop, do some research, make sure you're doing it the right way. Now, the pins 1 and 3, that is common. So I'm going to take an alligator clip, put it on that jumper, and I'm going to connect that to the common terminal on the control board. Now this other jumper, that is going to be for 24 volts. So I'm going to put my alligator clip on there and go directly to the R terminal on the control board. Now, I did mention earlier all these signals along this wire, they're all DC signals, but we can use a 24 volt signal just to wake the motor up. We're not going to have any control over it. So if the motor does start, it's going to default to whatever programming logic is in there. So it can start up at idle speed as if you're just running the fan, or it could run full speed like second stage cooling. All right, so now I have everything set up. I should be able to turn my power back on and the motor should start. And there you go. Now, if you can get the motor to run, next thing you want to do is you want to check the cheapest part between the expensive motor and the expensive control board, and that is the harness here. So what you want to do is just want to ohm out each wire end to end one by one. Make sure you're not reading any resistance or open line on any one of them. If you are, it's time to replace them. So that's pretty simple. You just put probe on, we'll start with pin 1 there, blue wire on one end, blue wire on the other, and I should read 0 ohms. And we're good. And I would just do that through all the pins just to make sure the harness is good. At that point, your motor's starting up, your harness ohms out just fine. Problem is most likely control board. But if your motor's still not starting, now it's time to actually dive in the motor. And the reason why I wait this long to do it, because it's not always easy to get into those things when they're actually inside the unit. So I try to save that for last. So to open up the motor, we have 2 bolts here holding it in. We're just going to take those out. And our module should come right off. So what we're looking here is our connector block. This brings in the 120 volts and the communication signals. Next, it'll go to this black disc here, and that is a thermistor. So this is a surge limiter. When this is cold, it has a higher resistance value. So when the motor first starts up, it's going to want to pull this big inrush of current in, and this thermistor prevents that with that high resistance. But once it warms up, the resistance drops, and the motor can pull whatever current it needs. So this is kind of like protection. Now, these thermistors, they're a very common fail point, and you can test them by ohming them out. But you want to make sure that these capacitors you see over here on the side, they bleed out. They do have bleed out resistors, so they will discharge, but you have to leave it unplugged and unpowered for at least, I would say, 15 minutes before you ohm out that thermistor. Now, what you should read will vary on what different types of motors. Sometimes you might see 4 to 12 ohms. Sometimes you might see them as low as 1 to 3 ohms. But basically what you're not looking for is either OL, that means the thermistor is bad, or you're reading very low or no resistance at all. Now, if you're not reading any resistance at all, the chances are that the module is still probably bad, even if you were to replace that thermistor. But if you're reading OL, it might be worth replacing that thermistor, soldering in the exact same replacement, and it's possible you could save the module if you have the means to do so. It then goes through the cleanup process, kind of like we did with the low voltage. So it goes to a rectifier diodes, which we can't see here. It's underneath the heatsink, but it converts the 120 volts AC into a pulsating DC signal. And then it goes through this black core here with the windings on it, and that is a choke. It cleans up all the electrical noise on that signal. Then goes through these brown cans here. That is our capacitor bank. And that takes that pulsating DC signal and turns it into a nice steady DC voltage. And then underneath all this, you can't see it, it turns that DC voltage back into 3 separate alternating current signals. So what we're doing here is we're simulating 3-phase power. Now, the reason why we turn it from AC to DC is so we can clean it up. And then when we turn it from DC back to AC, we can control those AC signals by modulating the DC voltage. So when we turn that DC voltage up, all 3 of those AC signals get stronger. We create bigger magnetic fields, and the motor runs at a higher speed. So we can adjust it by modulating that DC voltage as the logic plays out. And those 3 individual AC signals get sent to each winding on the motor, 3 windings, and that's the 3 wires we see here. These 3 blue discs we see over here, those are surge protectors. It's just another level of safety to protect the circuit. Now, one of the first things I want to do when I open this module up is I want to check the windings on the actual motor itself, make sure the motor's not bad. So to do that, I'm going to disconnect this Molex plug with these 3 wires going to it from the module. So to ohm out the windings on the motor, I'm going to put my multimeter in the ohm, go ahead, test my leads, make sure those are good. And then I'm going to test in pairs of 2. So I'm going to go from the black here to the blue. You see I'm reading about 4.7 ohms there. I am then going to go from black to red, and I'm reading about 4.5 ohms there. I am then going to go from blue to red. You see I'm reading about 4.6. So all 3 of these readings should be close to the same, just like a regular 3-phase motor, and they should all be within about 10% of one another. What you also want to do is you want to check each winding to ground, make sure you don't have anything shorted out. So you just do this one by one right to the grounded casing, and you should read OL. If you're reading 0, you have a shorted out winding. So everything checks out here. We know the motor is okay. And so now it's pretty much down to the module being bad.